Alright guys, so now that you've learned data pre-processing, it's time to start with regression. And basically with regression problems, you're going to be looking for things where you have a sliding value. Something like height, something like weight, something like price, something that's on a scale, that's a sliding value. Not something that's, say, categorical, like, either this is a mouse or this is a cup. It's not somewhere in between. Whereas with price, you can have stuff in between. And that's what we're going to use regression for. Regression is a way for us to, given a set of values, try to predict another set of values. So, put simply, the easiest and simplest, most vanilla regression algorithm out there is going to be simple linear regression. And this algorithm is super easy, super fast, and actually pretty helpful in a wide variety of circumstances. Basically, you have an X, you have a Y, you have a scatter plot of data, and then what you want to do is you want to plot the line of best fit so that given a new data point, you can predict that data point's X or Y. And so just to show you what I mean, what we are going to be doing is we are going to be predicting the heights of sons based on the height of their fathers. So as we all know, intelligence is hereditary, which means that father height and son height are going to be correlated. So if you go to Kaggle, or I've also pre-processed this data and it's in the GitHub for this course, you can see here that we have father and we have son. So we have the father height and the son height. And what we want to do here is we want to predict the line of best fit so that given the height of, say, the father, we can then predict about where the son's height is going to be. And this is a really powerful, really interesting implementation of linear regression. So let's get to it. The first thing that we're going to do is connect our runtime. So I'll let Google Colab do that. And then while it's doing that, we need to upload our data. And remember, you can get the data from the GitHub or you can pre-process it yourself. This is in a TXT format, and I converted it to a CSV format, which is going to be easier for the algorithm to read in. So if we just upload father-son-height.csv into our runtime, now what we can do is finally get our data set and import it into Colab. So the first thing we're going to say is import pandas as PD, and pandas is going to handle our data for us. We'll say our data set is going to equal to pd.read_CSV, and we are going to input the father-son-height.csv. Okay, so now that we have that done, what we need to do is we need to get an X and a Y. So if we open up our father-son-height CSV here in Colab, you can see we have father and we have son. So that's 2 columns and we have about 1,000 entries. So all we have to do here is we'll say our X value and we'll say it's equal to data set, and inside these square brackets we're going to input the string father because that is the name of the father column, and we're going to say dot values, and then our Y is going to be equal to data set son dot values. So our X is the father height, and then from the height of the father we want to predict the height of that father's son. Awesome. So we'll run that. Looks like everything went well. Next, what we're going to do is build the linear regression model. In order to do that, we're going to say from Scikit-Learn dot linear model. We're going to import linear regression. All right, sweet. So now all we have to do is create the model. And since we're going to have multiple models in this Colab file, I'm going to name our model lin_reg. And we're going to set that equal to linear regression with open parentheses. Now all we have to do to train our model is say linreg dot fit, and we are going to fit our X to our Y. So we'll run that. And you see right here we have an error. It says we need to reshape our data either using array.reshape or doing something else. And so this is actually a very common error in Colab. You'll get this, and it's super easy to fix. All you have to do is just copy this, and then we are going to apply this to one of our data sets. So I'll apply it to the X value, And basically the idea behind this is that our data is either like this or this, but we need it to be like this and this and this and this. Basically all we're doing is we're just flipping our data so that it's horizontal instead of vertical, or vice versa. So we'll run the data set, and then now you see our model works fine. Now what we need to do is we need to plot it out. So in order to plot it, first what we're going to do is we're going to import matplotlib.pyplot as PLT. And let's just see what our data set looks like without the linear regression line running through it. So we're going to say plt.scatter, and we're going to have the x, we're going to have the y, and our color is going to be equal to blue. And then we'll just say plt.show. So as you can see right here, we have the height of a father, and then we have the height of a son here. And you can obviously see that there is a correlation, albeit not a very strong correlation between father and son. As we know, you can't perfectly predict the height of a child based on the height of their father, but there definitely is a correlation here. And what our linear regression model is doing is it's plotting the line of best fit that most perfectly matches this data set of the correlation between father and son. And so in order to get our line to show up, we're going to say plt.scatter, or excuse me, plt.plot, and we are going to plot x for the x value, and the y value, instead of being our known y's, we're going to have our predicted y's. So we're going to say len reg.predict, and we are going to predict x. And then let's also make the color equal to red, because that'll show up nice on the blue. And then we'll make the line width equal to 4. And if we run that, you can see we have our linear regression line going through the scatter plot. And you can see here that this is a pretty good representation of our data, albeit it's not perfect, but then again, the data is pretty messy, so that's to be expected. Now, you may be wondering, okay, that's great, but what if our data is not just a straight line? What if our data would better be fit if it was, more like a curvy line? And for that, we're going to need to do polynomial regression. So in mathematics, if we go to Desmos, you have the idea of polynomials and polynomial degrees. So for instance, right now what we have is we have a linear model. So we have y equals x. Now what if our data is more complex than that? What we have to do is we have to raise the degree of our x. So like x squared, or x to the third, or x to the fourth, x to the fifth, etc., etc., etc. Now in order to do that, it's really, really simple. All we have to do is say from Scikit-Learn.Preprocessing, we're going to import our polynomial features. Then from there, we're just going to say poly is equal to, and we'll say polynomial features. And then inside here, we'll set the degree equal to what we want our degree to be. So for instance, for a simple hoopy shape, I know it has an actual name, we'll set it to 2, and then as our model, if our data is more complex, we'll keep on raising the degree and see which degree works best on the data set. But as you can see right here, we'll just set degree equal to 2, and we'll say x poly underscore poly is going to be equal to poly dot fit underscore transform, and we're going to transform the x so that it is now polynomially represented. Now after that, we're going to say poly.fit, and we're going to fit x underscore poly to the y. Now we need to train our linear regression model on this new polynomial data set. So to do that, we're going to say len underscore reg underscore poly is going to be equal to linear regression, and then len underscore reg underscore poly dot fit, and we're going to fit the x poly to the y. So we'll run that. Okay, it looks like our model worked. Now all we have to do is represent it. So if I copy this code right here and then paste it down here, all I have to do is, instead of saying linreg.predict, we're going to say linregpoly.predict, and then instead of predicting the x, we are going to predict the poly.fit_transform of x. So we'll run that, and it's a little bit hard to see, but you can tell that at the far ends our curve flattens out a bit, so it's not just a straight line. And if we say raise the degree even higher, like let's say to the power of 4, you can see that the curve is a little bit exacerbated, where it gets a lot thicker towards the top as it sort of starts to level off. All right, that's great. But you may be wondering now, what if we don't just have an x and a y? What if we have several x's and we only need to predict one y, or some combination of that? And in order to do that, you're not going to be able to graphically represent the x and the y here on the scatter plot, well, at least not until the very end of the course, but you're still able to perform linear regression and see how accurate your data is. And so this is where we get into the concept of multiple linear regression. And for that, what we're going to be doing is we're going to be predicting graduate admission data, that is admission to a graduate school program, based on several factors. So I have here also from Kaggle a data set that I've pre-processed a bit called admission data, and it's in the GitHub along with everything else. And you can see right here we have a bunch of x's like GRE score, university ranking, all that stuff, and then the y that we're trying to predict is the chance of admission. Now, we could make this a classification problem by saying if they got in, then they're in the admission category, and if they didn't, then they're in the rejected category. But instead, you see here we have a sliding scale of how likely they are to get in. And so that's what makes this a regression problem rather than a classification problem. And so the first thing that we're going to do is we are going to import our data set. So I'm going to re-import all the libraries just in case you guys are coming back later and resetting your Kaggle runtime. So we'll say import pandas as PD, and we'll say our data set will now equal pd.read_CSV, and we're going to read the admission data.csv. All right, great. Now we set the x and the y. And in order to do that, we're going to do something a little bit different than what we did when we had just two variables. We're going to say x is going to equal to dataset.iloc, that's ILOC, and then we're going to open up square brackets. We're going to have just a colon, empty colon, and then here we're going to have our values. So what we want for the x is we want from the 0th attribute all the way to the 0, 1, 2, 3, 4, 5, 6th attribute. And then the 7th will be our y. So we'll say 0:6. And of course we want to put dot values at the end of that. And then our y will be equal to dataset.iloc. And we'll say empty colon and then just 7th dot values for the last chance of admit column right there. So we'll run that. And now, as I told you before, we're not going to be able to graphically represent this because we have multiple x's and just one y, and we can't see into 6 dimensions with our eyes, unfortunately, at this point in time. So in order to see how accurate our model is going to be, what we're going to do is we're going to train on part of the data, but then set another part of the data aside. And this data will be the testing data. The idea is that we don't want our model to know the data set really, really well, but then when it's given a new example, it has no idea how to generalize what it learns, and then it fails. And that's what this testing data is for. It's a little piece of data that's set aside that is meant to check if the model isn't overfitting. That is, if the model doesn't just really know the particular data points that it was given and can't generalize. And especially since we have a smaller data set, that means that we're much more prone to overfitting. We're much more prone to the model being inaccurate. So in order to fix that, what we're going to do is we're going to have to split the data set. And luckily, Scikit-Learn makes this super, super easy. And even if you're not using Scikit-Learn, most people use Scikit-Learn just for this feature. And that is to split a training data and a testing data up for us. So we're going to say from sklearn.model_selection, we're going to import train test split. And then we're going to have our X train and our X test, our Y train and our Y test. Make sure that they're set equal to each other in this order. That's going to be equal to train test split. And we're going to say our X, our Y, and the test size is going to be equal to 0.2 or 20% of the data. Now, since we have 500 entries, that means that 100 data points will be set aside for testing the accuracy of our model. 20% is pretty normal. That's like the industry standard. If you have a lot of data points, then you can make it higher. If you have a little bit of data points, then you might want to make it lower. It really just depends, but generally you want the test data to be a good representation of the total training data without with the training data still having enough to train on. And usually that number is around 20% or 0.2 of the data set. All right, so with that being said, let's run it. And now what we're going to do is we're going to do the same thing with polynomial features that we did above, and we're just going to do it on multiple values. So we'll say from sklearn.preprocessing import polynomial features, and we'll say multi_poly is going to equal to polynomial features, and we'll set the degree at first just equal to 2. Then we'll say x_poly is going to be equal to multi_poly.fit_transform, and we are going to transform the x train. Next, what we're going to do is we're going to say multi_poly. Oops, I forgot a period there. Multi_poly dot fit, and we're going to fit the x poly to the y train. Now that we have that done, and it looks like everything ran okay, we're going to create our linear regression model. So we'll just say lin_reg_multi for multiple linear regression is going to equal to linear regression, empty parentheses, and then lin_reg_multi dot fit, and we're going to fit our x poly to our y train. Okay, so it looks like our model is sufficiently trained. Now, obviously, we can't graph it, so how can we tell how accurate our model is? Now, there are several ways to do this in linear regression. One way is to calculate the mean squared error. That is the difference between our predicted value and our actual value squared. And so this is just going to give us sort of a baseline of how far off our model is. So something like this, where the data points are all over the place, this is going to have a very, very high mean squared error, because you can imagine a data point that's all the way as an outlier. You take the distance between this from the line, and then square that. It's going to add up over time. But luckily, with this graduate admissions, we have a lot more features, and we can more accurately predict our chance of admission. So in order to show our mean squared error, what we're first going to do is we're going to get our predictions value. So we're going to say y_preds, which is short for prediction, is going to equal lin_reg_multi dot predict, and we're going to predict the multi_poly dot fit_transform, and we're going to do it on x test. So these are values that the model has never seen before. fit transform x test, and then we'll say Scikit-Learn import metrics, and then here we'll just print out metrics dot mean underscore squared underscore error, and we're going to show the difference between our y underscore test and our y underscore preds, because remember, we have the original value for what y is supposed to be in our y test. So we'll run that, and you can see our loss is 0.0005, which is it's a pretty good loss. It's a little bit hard to tell with the lack of data that we have, but that's pretty decent. Let's see if we can improve it by changing the degree of polynomial features. So let's say 3. And unfortunately, polynomial features, that's just something that you're going to have to work out on your own. There's no real way to sort of map the correlation in your head. I think that went up. Now let's try 4. As you can see, 4 is taking longer to train on the data set. But we'll run it anyways. And it looks like 2 is the best, because if I recall correctly, if we just go back to 2, yeah, 2 is 0.005, and the other ones were like 0.009. But yeah, guys, that's pretty much it for the basic regression techniques. You now know how to do simple linear regression, how to map polynomial features, and how to add multiple x and y features to predict a particular y value. But yeah, that's pretty much it. I hope you guys enjoyed this video, and I'll see you in the next one where we'll be working with classification, which is a little bit more popular in machine learning, I'd say. Sweet. Thank you guys so much for making it to the end of this video. As always, if you enjoyed it, make sure to hit that like button. Also, if you have any questions, comments, or concerns about what we did in this video, please leave them down below. Now, if I could have just one more minute of your time, I would like to tell you about a service that I've been using for over a year now called Scribd. Now, just as a side note, Scribd did not sponsor me to make this video. I just wanted to tell you about it. Put simply, Scribd is a lot like Audible, except for instead of being $15 a month, it's only $9, and instead of only having 2 audiobooks per month, you get an unlimited access to a plethora of audiobooks, ebooks, documents, and even sheet music and magazines. So for me, this was obviously a no-brainer, and right now, if you use the link in the description, you get 60 days free of Scribd, and I get 1 month if you sign up using my link. So that's why Scribd didn't officially sponsor this video. I'm just telling you about it so that I can get some free months, and I can continue learning, and you can also continue learning with your 60-day free trial. So thank you guys so much for making it to the end of this video, and I'll see you in the next one. Peace.